Let us try to derive the expression for the various parameters of full wave bridge rectifier. FWBR means full wave bridge rectifier. So we have already covered the working of bridge rectifier, but still those who are not knowing, for them I will repeat in only 1 minute. So this is the circuit. Here you can see the bridge is formed using the 4 diodes connected in the form of bridge. This is also the way in which the resistor can be connected, which is nothing but our load resistor. And here we are applying the AC input supply, and as a result same supply will be getting at the secondary. So this is the input we are calling as a V in, and V out I will draw right now. So now we know, let us consider this first positive half cycle. So during this first positive half cycle, what will happen? Point A will be positive with respect to point B. Due to this, we can see that this positive is getting connected here and negative is getting connected here. So as a result, what will happen? Here you can see the anode of diode D1 is getting connected with positive end, and here you can see the negative end is connected to the cathode of diode D2. Ultimately what will happen? Diode D1 and D2, they will become forward biased, while D3 and D4 they are becoming reverse bias. Here you can see the minus sign connected to anode. As a result, it will make it reverse bias. Similarly, the positive sign is connected to cathode of D4, that's why it will become reverse bias. So ultimately what I want to say is, in this case, that is during positive half cycle, diode D1 and D2 will conduct, while D3 and D4 both will act as a open circuit. So now you can see the D3 and D4, they are now open circuit, and D1 and D2 are forward bias, so they will be acting as a on switch. It means they will allow the current to flow through them. So as a result, the current will start flowing from point this A, then here it will come and it will try to find the path, as this is off, so no path is there. So it will continue its journey through diode D1. After coming to this point, again it will find that there is no path here as the diode is off, so the current will flow through this load resistor. Then again coming here, it has the path through D2, and after reaching to this point, it will go to the minus terminal, because we know the conventional current will try to flow from positive end to negative end of the supply. So this is the path through which the current is now flowing, right? So ultimately what we can say is the current is flowing like this through this, then this is the direction of the current, and finally it will reach here. So in this way we can say that during the positive half cycle, the current will flow and we will get this voltage across the load resistor RL. Now during negative half cycle, means this, what will happen? The point B, which was previously negative, will now become positive, and point A, which was previously positive, will now become negative. Now with this connectivity, we can now understand, now positive end is connected here, which is making this diode D3 forward bias. This is diode D3, okay, while this diode D4 is also forward bias. Its cathode is getting connected to negative end of the battery. What is the position of the another two diodes? So this diode D1 and D2, they are now reverse bias, and as a result D1 and D2 are now off. Hence diode D1 D2 will not conduct, means they will act as an open circuit, while D3 and D4 are now ready to make your current flow through them. So as a result, the direction for the current to flow will be like from B, then like this, it will come here. After coming here, it will find its path through D3, then here, from here it will flow through the resistor, and you can see the direction of the current is this, which is same as the direction of the current which was flowing during the positive half cycle. Then it will come here, then D4, and then back to the supply. It means that whether it's a positive half cycle or negative half cycle, it doesn't matter, the direction of the current flowing through this resistor is always same. As a result, the voltage which is generated in this resistor is always having same polarity. So that's why I can have the polarity of voltage generated like here it is positive and here it is negative, because the current is flowing from right to left. So this is the voltage which is generated across the load resistor and always having same polarity. So that's why during the negative half cycle also I get the waveform like this. After this, again this positive half cycle is coming, so the same cycle will repeat. D1 and D2 will provide the path for the current to flow. Again during negative half cycle, the same cycle I explained will repeat, and in this way this is the complete waveform I am getting in case of the full wave rectifier. Now, as far as the different equations or the expression for various parameters are concerned, we know that all the expressions we derived from the waveform. The very first expression that we derived is for the average DC load current, is also called given by IDC. So now we have derived the equation for same in case of full wave rectifier using center tap configuration. So now here the same waveform is there from 0 to pi. Here we can write the equation like it is I am sine omega t. Now this I explained in the derivation of the full wave rectifier using center tap. This waveform we write it, if you remember, we write this as a minus I am sine omega t. If you do not remember, kindly see those videos, right? So now after this, I think if you put all the values, you will get the same result as we have got in case of the center tap full wave rectifier. That's why I will not derive it once again. You can write the same expression as it is for the full wave bridge rectifier also. So that's why the equation for IDC will become IDC is equal to twice Im by pi, right? In the same manner, we have gone for the equation for IRMS in case of full wave rectifier using center tap type of configuration. So for that again the same expression will be there, and that's why the equation will become same as we have got there. So it is coming to be Im by root 2, right? So these equation are same, so you can either refer that videos or you can derive it here also. So now if all the equations are same, so why we are discussing? We are discussing here because now I am going to show you a minor change which we should consider. Like here this is Vm, right? So this will make the current Im to flow through the circuit. So in this case the equation of Im actually changes very minor. The Im is given by Vm divided by, now you know the resistances. Normal equation we have Rs plus Rf plus Rl. This equation you know. But here if you can see the difference, the thing is that what is Rs? Rs is the resistance of this secondary. What is RL? RL is this. Only here if you can see during positive as well as negative half cycle, every time two diodes are coming, right? During positive half cycle diode D1 and D2 are conducting, during negative half cycle D3 and D4 are conducting, and that's why in this equation we should take here twice RF, not RF, it is twice RF. So this is the minor change we should be considering. Remaining all equations can also be derived based on this, like we can derive the equation for the average DC load voltage which is given by EDC. So that we know it is given by IDC multiplied by load resistance RL. Then again putting these all values and you can solve further. Ultimately we can prove that this comes to be twice Vm by pi. So this already we have derived, so that I will not go once again to save the time. Now the last equation which remain is the equation for the efficiency, which is given like efficiency is equal to the ratio of DC power which we are getting at the output divided by AC power which we are applying at the input, right? So now again the DC power can be given like P DC is equal to the same equation which we used earlier also, IDC square into RL. And now what is the equation for IDC? This is here, and in this equation we have to put the value of Im. So that's why I will directly write here the equation for this Im I will take. So here you can see IDC is this, so that's why IDC square, so it comes to be 4 divided by pi square, and here Im square multiplied by RL. Now further, if you want, you can put the value of Im as here, which we have already derived, and that can be taken further. Then equation for PAC, that is the AC power which we are applying at the input, right? So for that, we know that we consider the RMS current, so it is I square into R, so I RMS square multiplied by resistance. So now again all the resistors we consider. So we know the equation means we have the three resistors RS plus RF plus RL, but only the new thing here is that instead of RF we should be considering twice RF, because every time the two diodes are coming in focus, right? So then again, the instead of RMS I should be putting this value here. So if I put this value here, I get the equation like it is Im square, then in bracket RS plus twice RF plus RL, and this whole will be divided by, here it is root 2, so it's a square, so it is divided by 2. Similarly, you can expand the equation for this if you want, and finally I will get the equation for the efficiency. Now here I will write here. So equation for efficiency is, now we know it is PDC by PAC. So this term divided by this. If I put that, I request you all to solve. I will directly write the final equation. I will be getting 8RL divided by pi square in bracket RS plus twice RF plus RL, right? So this is the equation. Now again, as our usual practice, we will neglect, what we will neglect? We will neglect RS plus twice RF. Reason you know, we will neglect RS plus twice RF, as RS plus twice RF is very small as compared to load resistance RL. So this is the usual practice. So what we are going to neglect this term. So if this particular term is, this is plus, so if this particular term is neglected, we are remaining with eta is equal to 8 RL divided by pi square into RL, right? So this RL will get cancelled and we are remaining 8 by pi square, and after solving this we will get one value. Now I will directly write in terms of percentage. So percentage value of the efficiency is 81.2%. It means it is same as we derived in case of the center type full wave type of rectifier. And also keep in mind that all this thing we are considering, means we are neglecting everything and all the ideal things we are considering, and still we are getting only this value. And that's why it is said that the maximum efficiency that we can have in case of full wave rectifier, this is maximum, it can be 82, means it is 81.2% only. It means that practically we won't be getting efficiency even 81%, right? Theoretically or ideally it is 81.2%. So here it is completed.